Alrighty, good morning everybody. Welcome back to Calc 1. Plan for today is I have a quiz for you on Standard 18. Then we're going to finish off Standard 19 by talking about the fundamental theorem of calculus. Biggest theorem of the semester, which is why it gets the most pretentious name. And then if we have time towards the end of the class, we might start Standard 20 and look at the net change theorem. I've got my usual office hours on Monday at 11 and at 2, my next office hours. As far as homework goes, we're going to have a quiz Monday over Standard 19. And I also put up a homework this morning, homework 21, that is due 2 classes from now, which just so happens to be not this coming Monday, but the Monday after Thanksgiving. So, a lot of time on that one, but you might want to do it this weekend, prepare for the quiz on Monday. And also, don't forget you do have a homework set due tonight. So, quick announcement. I plotted out the rest of the semester. We're going to get through standards 20 and 21. There is supposed to be a standard 22. I don't think we're going to get to it. So, I'm just going to cross it out. So what does that mean as far as mastery totals? Well, you still need 22 standards mastered twice, and so since that's now impossible, nobody's getting an A. No. I'll update over the weekend the syllabus with necessary mastery totals for each grade, so you know where you'll stand. But just know that that I do plan on there being 21 mastery or 21 standards now. Standard 20 is net change theorem. Standard 21 is use substitution. And then after that, that'll be the end of it. Any questions or comments before we get started for today? One day, a dog up on the farm is rounding up sheep. So it goes around, gathers all the sheep, gets them all back in the pen. And then the sheepdog reports back to the farmer and says, I got all 40 of them in here. The farmer says, 40? I thought I only had 38 sheep. The sheepdog responds, oh yeah, I know, but I rounded them up. Alrighty, and with that, it is quiz time. So go ahead and put everything away, and I will pass out the quiz.
If you would actually multiply that out, it would be a nice number.
Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. If you heard me say yes, because I always try and stop my timer, so like right on the second, and I got it this time. I usually don't. Personal success. Alrighty. So, if you recall, last class we talked about, we introduced this idea of a definite integral, where you have a function f of x and two values of x from x equals a to x equals b. We could talk about the definite integral of f of x over this interval is just going to be the area underneath the graph of our function f of x between our two values a and b. And if you recall last class, we looked at the example again of f of x equals x squared from x equals 1 to x equals 5. And we said that if you wanted to compute this definite integral, meaning find the area underneath the graph of x squared from 1 to 5, what we can do is we can take a limit as n goes to infinity of r sub n, our right endpoint approximation using n rectangles. Meaning that we know that if we use more and more rectangles, our approximation should give us something that's closer and closer to the actual area. If we take a limit as n goes to infinity, which if we do that, we'll end up adding a bunch of areas together like this, getting a lovely looking expression. We did a bunch of algebra, and it turned out that the actual area ended up being 41 and a third. If you also recall, I said that I was tricking you in the sense that standard 19 is not going to be about carrying out this process, adding up these r sub n's and taking a limit as n goes to infinity. Instead, what we're going to do is we're going to do something a little bit less algebraically intense. So if you remember, we said that the definite integral from say 1 to 5 of a function is just going to give us the area underneath x squared from 1 to 5, and that gave us something called the definite integral. What would we get if we just wrote out the indefinite integral of x squared? If we're not specifying an interval. So this is something we saw way back in standard 11, I think. What did it mean to take an indefinite integral of a function like x squared? Avery?
Find the antiderivative.
Find all the antiderivatives. But yeah. So Avery, what would all the antiderivatives of x squared end up looking like?
X cubed over 3 plus c.
Yeah, they'd be something of the form 1/3 x cubed plus c. And so this gave us our idea of an indefinite integral, which is finding all the antiderivatives of our function. And so if you think about it, these two ideas, finding indefinite integral and finding a definite integral, don't really appear to have that much in common with each other, if you ask me. And that definite integral of a function over some interval like this just is going to come out to some number, a single number corresponding to the area underneath your function between your two different values of x. Whereas indefinite integral doesn't come out to a number, it comes out to an entire collection of functions, a family of functions. Specifically, all of the functions that are antiderivatives of x squared. All the functions we can differentiate that would give us x squared in the end here. So we have two different notions of integral going on here. And it doesn't really seem like they may have that much in common with each other. Guess what? They do. And this is going to lead us to our biggest theorem of the semester, the fundamental theorem of calculus. I'm on page 3 now in the packet, if you want to follow along. And from now on, we're going to, since fundamental theorem of calculus is a lot to write out, even if we're abbreviating, I'm going to probably refer to it as the FTC, if you see me write it out. And what the fundamental theorem of calculus says is that there's an easier way to compute definite integrals using the idea from an indefinite integral of finding antiderivatives of the function you want to find your area under. Specifically, what the fundamental theorem of calculus says is that if little f of x is a function that is continuous over some interval of real numbers from a to b, and if we suppose that big F of x is an antiderivative of little f of x, then what will end up happening is that we can compute the definite integral from x equals a to x equals b of our function. And what we can do is we can plug in our endpoints into our antiderivative of little f of x and then just subtract them. So in other words, in order to evaluate a definite integral, rather than having to go through this nasty process each time of finding r sub n, taking a limit as n goes to infinity, getting a gazillion algebra things you have to do, instead, compute a definite integral and to find an exact area under the curve. Turns out all that we need to do is to take an antiderivative of our little f of x, plug in the endpoints, and subtract. So let's put this to the test with this function we just did. See if we can come out to the same answer of 41 and a third. So let's look at finding the area under f of x equals x squared. And we want to find the area under it from x equals 1 to x equals 5 again. This time using our fundamental theorem of calculus. Emily. Avery found all of the antiderivatives of x squared earlier. He said that they were all of the form 1/3 x cubed plus some constant. What's your favorite antiderivative of x squared? 1/3 x cubed plus 4. Okay? That's certainly a function that's an antiderivative of x squared. We differentiate, the 1/3 x cubed will become x squared, and the plus 4 will go bye-bye. So we can say, since big F of x equals 1/3 x cubed plus 4 is an antiderivative of little f of x, that's going to tell us that if we want to compute the definite integral from 1 to 5 of our function little f of x, which is x squared, all that we have to do is take big F of 5 minus big F of 1. Which if we evaluate that out, is going to come out to what? It's going to be 1/3 times 5 cubed plus 4 minus the quantity 1/3 times 1 cubed plus 4, which we do a little bit of algebra here. We'll get 5 cubed is 5 times 5 is 25 times 5 is 125. We'll get 125 thirds plus 4 minus 1/3 minus 4.
Cancel the fours.
Oh, hey, ain't that convenient. So what'll that give us? 124 over 3, which my spidey sense is going to tell me 41 1/3. Riley, which do you prefer? Did that feel easier to you, what we just did? Or would you prefer to do the whole limit as n goes to infinity of r sub n process that we did yesterday?
Definitely the one we just did.
Or Wednesday. Days are hard. Yeah. This is a heck of a lot less work than what this was. When we did this process yesterday, it basically took up like the entire 2 boards worth of work, of space, just finding a general formula for r sub n, looking like something like this. We had to calculate our delta x, we had to look at our intervals, we had to we had to plug in f of 1 plus 4 over n, 1 plus 8 over n, we had to do a bunch of foiling, we had to do a bunch of refactoring, we had to use Gauss's formulas for finding sums like 1 plus 2 plus 3 all the way up to n, we had to simplify, we had to do so much algebra that our heads spun. I know grammar. Or we could just take an antiderivative, plug in our endpoints, and subtract. I personally think that this way is much easier. I agree with you, Riley. Emily, did it matter which antiderivative you chose? Why not?
Cancel out.
Ooh, what canceled out?
The value you plug in for C.
So you chose the constant term of 1/3 x cubed plus 4, and it turned out that this plus 4 ended up not mattering because when we plug in big F of 5, we added 4. When we subtracted off big F of 1, we subtracted it away. And it turns out no matter which constant term Emily had chosen for her antiderivative, it would have just gotten canceled out at this step anyways. I think I had, in my notes, I chose plus 2, and I had a plus 2 minus 2 that canceled out. So, turns out that our choice of antiderivative doesn't matter. As whatever constant term we choose at the end will just get canceled out when we do our subtraction. Because the constant term just gets canceled out. So we could have chosen any antiderivative. 1/3 x cubed plus 4, 1/3 x cubed plus 2. If you're feeling a little bit frisky, 1/3 x cubed minus 17,000 pi. We would have gotten a negative 17,000 pi and then a plus 17,000 pi, so they would have canceled out. If you want to be boring about it, you could have just used 1/3 x cubed by itself. And then we just wouldn't have had any constant terms to cancel out. But the moral of the story is this process works and gives us the same answer no matter which antiderivative we end up using for our original function. And here we're definitely relying on the fact that any 2 antiderivatives will always be the same except for their constant term. And since the constant term will just get subtracted off either way, it doesn't matter. If you want to make your life easy but boring, just do the one with a constant term of 0. Or you could have a little bit of fun and add some constant term in, pick whatever one you want. It'll always come out to the same thing. Any questions or comments? Let's do another example. squared should have. So another example that we kind of looked at in our previous packet was the function g of x equals 25 minus x squared over the interval x equals 0 to x equals 4. Which, when we graphed out, ended up looking something a little bit like this. And in standard 18, the last standard, when we were using rectangle approximations to this area underneath the curve, we found that our actual area was something between 70 and 86. Where I think we used a left endpoint and a right endpoint approximation with 4 rectangles to get that our actual area has to be something in between these two values. So now we can compute the actual area. The actual area is going to be if we take an antiderivative, or if we take, definite integral from 0 to 4 of 25 minus x squared. Let's see. Zach, what's your favorite antiderivative of 25 minus x squared?
25x minus x to the third over 3.
No constant term?
Nope, just plus 0.
Lame. 25x minus 1/3 x cubed. Dr. Ersta, what is this vertical bar with the 0 and 4 you just wrote? So this is sort of a shorthand notation. This symbol right here is just a and what this notation means is just plug in 4, plug in 0, subtract the two things that you end up getting. Plug in 4 and 0, then subtract. Just to save us a little bit of extra time so we don't have to write out, since big F of x equals 25x minus 1/3 x cubed is an antiderivative of f of x, then we know that this definite integral comes out to big F of 4 minus big F of 0 equals, and then blah, blah, blah. So this is just sort of a shortcut sort of notation that you can use for actually saying, plug in your two endpoints, 4 and 0, and then subtract. Is to put a little vertical bar after your expression, plug in 4, plug in 0, and subtract your two. All right, so if we plug in 0 and 4, we'll get 25 times 4 minus 1/3 times 4 cubed minus 25 times 0 minus 1/3 times 0 cubed. 25 times 4 is 100. 4 cubed is 4 times 4 is 16 times 4 is 64. Sam, what are we going to get if we plug in 25 times 0 minus 1/3 times 0 cubed?
0.
Hey, these are just 0. So those terms don't end up mattering. Which is going to be 64 thirds is what? 21 and 1/3? 21 times 3 is 63, plus 1 is 64. So that's going to come out to 78 and 2/3 is our final answer. What do you think? Is that an answer that fits snugly in our interval that we found in standard 18 for what the actual area should be? John?
Yeah.
Certainly looks like it. 78 and 2/3 is certainly in between 70 and 86. In fact, it's almost exactly in the middle. Exactly in the middle of the two would have given us 78, but 78 and 2/3 is still pretty close to the midpoint between 70 and 86. No fuss, no muss, no cocoa nuts. take an antiderivative. Doesn't matter which one. Zach chose the one with no constant term at all on the end, which is probably the easiest way to do, and honestly what I recommend. Because if you have a constant term, you'll just end up subtracting it out. Like if we had said 25x minus 1/3 x cubed plus 27, we would have had a plus 27 here, a plus 27 here, and then this positive 27, we would have ended up subtracting a 27, and it just wouldn't have ended up mattering in the end anyways. And we got down to an answer with a minimal amount of algebra. Still a little bit of computation. You still have to find your antiderivative, find an antiderivative, plug in the two endpoints into that, and then subtract. But much, much less than if we were to try and do the whole method from last class of take a limit as n goes to infinity of r sub n process. Any questions or comments? Let's do one more example. And I'm gonna leave you the two examples on this page to kind of work on as your own as a practice problem. Ooh. Practice problems. Ooh, indeed. Let's get spicy and do a little bit of trig. I want to find the integral from pi over 2 to 3 pi over 2 of the function f of x equals sine of x. So first of all, I need an antiderivative of the sine function. Anybody give me a function whose derivative comes out to sine of x? Well,
Would it be negative cosine x?
let's see, I think cosine of x would have a derivative of negative sine of x. So negative cosine of x should have a derivative of negative sine of x, which I think will give us what we want. Sorry, Rachel, just trying to spread the wealth of participation a little bit. So, antiderivative that Will chose, he chose the most boring one of just negative cosine of x. Watch your tongue. Instead of getting a little bit more fun and saying, oh, we can do negative cosine of x plus square root of pi over 17. 0.2. Negative cosine of x is probably the easiest one. So if we plug that in, we'll get negative cosine of 3 pi over 2 minus negative cosine of pi over 2. I forget, did I give you a unit circle on this one?
This is 0 minus 0.
Oh, but Zach's got me covered. It's not 0 minus 0. It is negative 0 minus a negative 0.
Not bad.
Which is, yes, just 0 minus 0, which is 0. What does that mean?
It's got no area.
There's no area. So what does that mean? It's just, are we saying that sine of x just acts as like a flat line, y equals 0, something with no area underneath it at all the way from 1 to 5?
There's an equal positive area as there's a negative area.
Negative area? What the heck is negative area?
Above the x-axis and below the x-axis.
Ooh, there's equal area above and below the x-axis? Let's take a look at a graph of sine of x just to see what's going on here. Joseph, I think you, I think you might be onto something here. If we graph this out, do a graph of sine of x from pi over 2 to 3 pi over 2. So let's see, pi over 2 is here, this will be at pi, this will be at 3 pi over 2, this will be at 2 pi, and then the graph continues. So if we look at the area underneath sine of x from pi over 2 to 3 pi over 2. That's going to be this area and here. Well, it certainly doesn't look like there's no area underneath sine of x from pi over 2 to 3 pi over 2. I see this one kind of chunk of area right here, and another chunk of area down here. And so, Joseph, can you repeat what you were saying earlier about why you think that this total area just turns out to be 0?
There's equal area above and below the y-axis, or x-axis.
Yeah, I would say so. So, I'm going to call this A1, I'm going to call this A2. And what's going to turn out to be the case is that that area above the x-axis counts as positive area towards our finding the total area under the curve. Positive since it's above the x-axis. A2 down here, the area from pi to 3 pi over 2, is going to count as negative area. Since it's below the x-axis. And so, as Joseph has pointed out, it turns out that the amount of positive area A1 gives us is going to be exactly the same as the amount of negative area that A2 gives us. So if we combine these two sections of area, they're just going to completely cancel out and leave us with an answer of 0. So in this case, we could say that A1 and A2 are just going to cancel each other out to leave 0. So through most of the semester, when we talk about the areas as like the two-dimensional area of some shape, we're used to sort of thinking about area as being something that always has to be positive. Because if like this is a real-world situation, like our optimization problems in standard 17, we wouldn't want to say, I have a fenced-in area of negative 20 square feet. It wouldn't really make sense as a real-world problem. But when we're looking at the area that can be given to us by a definite integral like this, that area could possibly come out to be something negative, or 0 even. And if that happens, if it comes out to something negative, that just means there's more area underneath the x-axis than there is above the x-axis. Because the definite integral is always going to treat area above the x-axis as positive area, and area beneath it as being negative area. Giving us our integral formula, which graphically kind of illustrates the exact same result that we found using the fundamental theorem of calculus over here, which is that the total area underneath our curve comes out to 0. Any questions or comments? Okay, that's it for standard 19. So on the standard 19 quiz, no, I'm not going to make you do any of the big nasty take a limit as n goes to infinity of r sub n stuff. I mean, I guess theoretically I could, but I'm not going to. Instead, what you should be familiar with for the standard 19 quiz, I would say, is understanding what does the fundamental theorem of calculus say, how does it work. So you're likely going to get a problem or two where you actually have to compute a couple of definite integrals. And then maybe be familiar with questions like, why is it possible to get a negative answer for our area? Or why does it not matter which antiderivative we choose in computing the definite integral? So questions like that corresponding to what we did today are what I'm would ask about on a standard 19 quiz or test question, not the stuff we did yesterday. Stuff we did yesterday, I just kind of wanted to illustrate to you, if we didn't have this fundamental theorem of calculus, how horribly nasty finding the actual area would end up being. Because what we did yesterday was just for x squared. Can you imagine if we had tried to go through that whole process with a trig function? It would not have been pretty. We ended up needing to use like almost all of our trig formulas on that trig sheet I sometimes give you. And yes, if I give you something involving trig functions on a quiz, I'll make sure to attach a copy of the unit circle for you. Any questions or comments before we move on to the net change theorem? All right, in that case, go ahead and pass this out. One, two. All right, second to last standard of the semester right here. Just so you know, kind of what my plan is on Monday we'll finish off standard 20, and then week after Thanksgiving, Monday and Wednesday we'll do standard 21, which is U substitution, which is sort of an integration technique. And then Friday, the last day of class, midterm number 3. The last day of the semester, yes, I'm giving you a midterm. It'll have one question from every single standard, and it'll be up to you to determine which ones you want to do. And then the final exam will be pretty much the same as the last midterm, except you'll have a full 2 hours for it instead of just 65 minutes. It'll be the same in the sense that both the last midterm and the final exam will have a page on it for every single standard.
When is the last day we can come in to retest?
Ooh, good question. When's the last day we can come in to retest?
Limited times during exam week. I'm not saying it's a good idea.
I'm saying that's a terrible idea. Might be a good idea for you. It sounds like a horrifying idea for me.
Well, it's too expensive.
I'll give you one retest during finals week.
Fair enough.
That'll be your last chance to earn a master. Say what?
It's stressful. You have like one left.
Yeah, you're on the last one, and you just
Yeah, but no pressure. It's all that stands between you and
It's this
getting
one.
an A or an A minus.
It's this one, and you just get to the things. Next to the third, do what we do at the beginning.
Yes. you can.
How many masteries do you need to get an A minus?
I don't remember offhand. I think if you get like all but 2, maybe you'll get an A minus, something like that. I forget what the requirements for B. I should just make a table that has all the grades A minus. All right, I tell you what. Over Thanksgiving break, maybe this weekend if I have time, I'll come up with a table that has exact grade breakdowns for pluses and minuses as well. But I will say to get an A, you need 42 masteries.
Or we have 2 that we get from doing homework, right?
Correct. So up to 2 of those can be from doing the homework. As a reminder, if you have an 80 to 90% on your final homework score, you get +1 bonus mastery. If you have over a 90% on your final homework score, you get +2 bonus masteries. But in order to get an A, you need all 42 masteries. Or potentially, you have up to 2 of those can be from the bonus masteries. All right, let's do some more math. Alrighty. Mackenzie. When we were doing standards 15 through 17, our maxes and mins standards, did you prefer the ones where we were working on word problems or the ones where we were just saying, here's a function f of x, find local maxes and mins?
Just a function.
Just the function. Well, I have good news for you. Standard 19 is the here's a function, just compute some stuff. Standard 20 is the word problem version of standard 19.
Let's go.
But before we get into any of these word problems, we have a new theorem. Which I'm going to call the net change theorem. And what the net change theorem says is that if we have a function f of x, where f of x is differentiable everywhere in the interval from a to b, then it's going to turn out to be the case that if we were to integrate f prime of x from x equals a to x equals b, we're just going to get f of b minus f of a. So in other words, integrating the derivative f prime of x is just going to give us the same thing as if we plugged in the endpoints to our original function and just subtracted them. Does this theorem look familiar to anyone? Or dare I say, similar to any other theorems? Logan?
Basically just the same thing, except instead of saying f prime, it would just be f of x in the previous one and then a capital F.
Yeah, this is really just the fundamental theorem of calculus again, just replacing little f of x with like big F of x. Or vice versa, replacing big F of x with little f of x. Since little f of x is certainly going to be an antiderivative of little f prime of x, any function is always an antiderivative of its own derivative. Basically, this is just saying you can plug in, if you want to integrate the derivative of your function, just plug in the endpoints and subtract. It's really the same as the fundamental theorem of calculus, just replacing big F of x, our antiderivative, with little f of x. And then little f of x is getting replaced with little f prime of x. So this isn't really a new theorem, it's just the same theorem but being presented in a slightly different way. And this is something we've seen before, where if you have a function f of x and you plug in the value of the function between two different points and subtract, this is actually something we've seen back in not standard 19 or standard 18. Standard 1 of the semester, you saw expressions that look like this. Mackenzie, I see you nodding. So where have we seen an expression of plugging in the function at two different points and subtracting?
Average rate of change.
Yeah. We saw that show up as part of the average rate of change formula. And what did we call just the part where we subtract the function at two different points? Something in distance. I'll give you a hint. I'll give you a hint. It's in the name of the theorem.
Rate of change. The average.
Yeah. Net change. Sorry, that's what I was going for. Yeah, it gives you the net change in your function between two different values, x equals a and x equals b. So what the net change theorem is really telling us is it's giving us a way to sort of rewrite the net change in our function from one point to another point. It's saying if you want to compute net change from a value x equals a to x equals b, instead of just taking f of b minus f of a and subtracting like that, Another way you can compute that is by taking an integral from a to b of your derivative function. Integrating f prime of x from x equals a to x equals b. So let's take a look at it and see what on earth does that actually mean? Or why on earth do we want to compute net change using a definite integral when we could just plug in our two endpoints and subtract? Turns out that this is going to be useful to us in a bunch of different contexts, where being able to say that these two expressions are equal to each other is going to allow us to integrate when we have a formula for f prime of x, but are maybe not given a formula of f of x to start with. So where's my copy of the packet? Oh, here it is. So let's look at this problem on the front page, where we have a motor on a boat that started at t equals 0 hours, and our boat is going to consume gas at a rate of r of t equals 10 minus t cubed gallons per hour.
It's 5.
It's 5 in the packet?
Yeah.
Oh, no it's not, it's 10.
Alright, fair enough.
Proof's in the pudding. I just wrote 10 on the board. If you look at my version of the packet, clearly you could see it's 10 written out there. Typo in the packet, it should say 10, not 5. And the reason why is because I realized after I printed this that if it's 5 minus t cubed, then the problem doesn't make sense, in the sense that at some point in time after we start driving our boat is going to cause us to gain gas back instead of lose it, and that doesn't really make any sense.
Happens sometimes.
Happens sometimes. If you're driving through a lake of gasoline, maybe. And if you're doing that using like a motorboat, I do not recommend using something that sounds like it's going to make the entire lake explode. So, how much gas is used up in the first 2 hours? So in other words, we graph this out. We sort of have this function that's going to tell us something about how much gas we're using up at a given point in time. That at say time t equals 1, we're using up gas at a rate of 9 gallons per hour. So let's graph this out. This 10 minus t cubed. It's going to look something like this, from 0 to 2. So I want to define a function. I want to say, let capital R of t be the amount of gas used in gallons. Let's say the total amount of gas used after t hours. So big R of 1 would be how much gas did we use up in the first hour. Big R of 2 would be how much gas we used up in the first 2 hours. So I think that's what we want to find actually, is big R of 2. Big R of 17 is how much gas we would use up in the first 17 hours. Spoiler alert, we'd run out of gas by then, probably. So here's my question. These are not the same function. This one's measuring something in how much, what's the rate at which we're using gas. It's given in gallons per hour. Big R of t is just going to be the function that says, after t hours, how much gas have we used up? What's the relationship between these two functions? Between the function that says how much gas have we used up versus the function that tells us the rate at a given point in time at which we're using up the gas. Well,
R of t is the derivative of whatever the line you drew on the left.
this function is the derivative of that one?
Oh, I see. Okay, so capital R of t, or R of t is the derivative of capital R of t.
This is the derivative of that?
Yeah.
Joseph, what do you think?
Yes.
Do you agree with that? Yeah. Going way back to how we originally defined the derivative tells us the instantaneous rate of change of our original function. So if little r of t is telling us the rate at which gas is being used up, an instantaneous rate of change of how much gas we're using, and that's going to tell us that big R prime of t is going to be equal to little r of t. And so the function that we're given is not going to be a function that tells us big R of 2, which is sad. If we wanted to find big R of 2, we can't just plug in 2 here because that tells us the rate at which we're using gas at 2 hours, not how much gas have we used in total after 2 hours. So we're given a formula for big R prime of t. And I think what we want to find the next change in the amount of gas used after, or let's say from t equals 0 to t equals 2 hours. So in other words, we want to calculate big R of 2 minus big R of 0. But the problem is we don't actually have any function for big R of t. How can we compute big R of 2 minus big R of 0 without even having a formula for big R of t in the first place? If all that we have is a formula for big R prime of t. When?
You have to take the definite integral from 0 to 2 of little r of t.
Yeah, exactly. We can use the net change theorem, which put over here to give myself some more space. The net change theorem is going to tell us that if we take big R of 2 and subtract off big R of 0, that's going to be the same as integrating from t equals 0 to t equals 2 big R prime of t, and that is something we do have a formula for. It's going to be an integral from 0 to 2 of 10 minus t cubed. So in other words, to calculate our net change used, we don't have a formula for the amount of gas that we have in our tank at 0 hours and 2 hours. But if we integrate from 0 to 2, our rate of change, that should give us that same information at the end. Ryan, what is your favorite antiderivative of 10 minus t cubed?
10t minus t to the 4th over 4 plus 10.
Plus 10? We'll get a little bit spicy. I'm on board. 10t minus 1/4 t to the 4th plus 10. Evaluated from 0 to 2. Which means we're going to need, 10 times 2 minus 1/4 times 2 to the 4th plus 10. Minus 10 times 0 minus 1/4 times 0 to the 4th plus 10. Here, again, I'm using this vertical bar 0, 2 to mean our shorthand for plug in 2 and 0 and then subtract what we get. 10 times 2 is 20. 2 to the fourth is 2 times 2 is 4, times 2 is 8, times 2 is 16, divided by 4. It's going to give us a minus 4 here. Plus 10. Minus 0, minus 0, or plus 0, excuse me, minus 10, because this minus sign gets distributed across. Emily, what's so funny? Am I making some mistake here now?
No, it's just that you corrected minus 0 plus 0.
Oh, yeah. Well, we got to have our plus and minus signs correct here. Heaven forbid we subtract 0 instead of adding it. Oh, hey, plus 10 minus 10, that's convenient. Maybe that 10 term that Ryan used didn't end up mattering too much. We're going to get 16. 16 what's? Someone said something. Gallons. 3 gallons of oil. Yeah, because we're looking at how much gas was used up during 2 hours, and the amount of gas used is being measured here in gallons. So the moral of the story is, we can sometimes use the net change theorem in situations where we don't know what our original function is, but we know what its derivative is to calculate net change of the original function. Alrighty, y'all have a good weekend, and I'll see you all on Monday for our last pre-Thanksgiving class.